It's like neck and neck, you know.
Okay, good evening, everyone. So lesson 18, this lesson, we will continue to discuss reading sums, the area under a curve, and we will start to connect this soon with antiderivatives. So first a question. If we know that fx is antiderivative for little fx, I remember that means that the derivative of big F is equal to little f, then how do we know that all other antiderivatives are of form fx plus c, so I said this is by the mean value theorem. So to be precise, if you want to look back at the argument, it's in lesson 14, one of the corollaries. So I won't go through the argument again now. If you are interested, you can look back, but the thing to remember at this stage is the definition of derivative, and that if I know one antiderivative, I know them all. They are just of the form where C is constant. Okay, so I'm just checking in to see if there are any questions, more questions or comments. So, midterm, marking is in progress. More feedback next week. In particular, I will talk a bit about graphs. I saw the feedback about there being a lot of graphs in the midterm. Okay, so And there, let's continue. And go back to studying Riemann sums in some more detail. So we start with a function f on a closed interval AB. So say function f. And basically we want to calculate the area under its graph. But it's a bit more complicated than that. Let me find the example we had from last time. So here we are. So an example of a function like this. And we see it can be positive or negative. So actually, I'm just going to copy in what we had from last time. The first step of the construction, and that's to pick sub-intervals. So I pick some numbers between A and B. I'm calling them x1 up to xn minus 1. And the ends of the interval A and B I'm calling x0 and xn. So we have intervals x0, x1, x1, x2, and the last one will be xn minus 1, xn. Because remember, x0 is equal to A, and xn is equal to B. So for this, we have some notation. We call this a partition of the interval into parts. We write big P is partition. And I just write my numbers like this. And for the lengths of the intervals, I'm going to write delta, so change in x. Oh, strange noises happening. Going to check the microphone. Hey, yes. Oh, I see that some people have their microphone switched on. Well, please turn off their microphones. Thanks. I think it's okay. Okay, I think microphone will be turned off now. Okay, so I'm going to write the lengths of the intervals like this. Delta x1, x1 minus x0, delta x2, x2 minus x1, all the way up to what's the last one? The last one is delta xn, because xn is the last number. So we have these. So now we make an approximation of the area under the curve using boxes on these intervals. So a picture to show you what I mean. Not that one, this one. Yeah. Okay, and I'm going to put this on a new page. Right. Okay, so we can see in this picture the same function, and I've taken x0 on the left and xn on the right, and in between I've taken x1, x2, and so on. And these give my intervals. So we can see 8 of them, but you can imagine there could be more. And the way I make the approximation is by picking inside each interval C1, C2, and so on, taking the value and taking a box with that height. So then my estimate for the area is this Riemann sum. So definition. The Riemann sum SP, so remember P is the partition, the choice of intervals, is the sum using my sigma notation, and I'm going to sum over all the boxes. There are n boxes here, and I'm going to sum over the area of the boxes. And that's FCK times delta XK. I'll just write this is the box area. And this is for our function f on the interval a to b. So note we choose CK, well, let's write it out. C1 we choose to be in the interval x0 to x1. C2 in x1 to x2. So this is what the picture is showing. And the last one would be Cn in xn minus 1 to xn. So we have a free choice. We can choose an easy place to calculate the function. And we'll see why it's important. So recall, we were saying last time, when value of f is negative, area of box is taken to be negative also. And we saw why that made sense when we're calculating an area under a graph. It means that the area also lets us calculate an average value. Okay, so I'll start another page. Idea. As the intervals become smaller, SP approaches area under graph. So a picture of this. So first we had something like 8 intervals. Now we have something like 16. We could keep doubling. And you can see that the boxes are closer and closer to the actual graph. So we hope that SP approaches the actual area under the graph. But the question is how to measure how small the intervals are definition. We write it like this. It's the maximum delta xk, so the maximum width of an interval for the partition P. So let's give an example of this. Yeah. So for example, for this P, the maximum delta x, well, let's have a look. It's 0.5. So now I'll give the definition using this definite integral as limit of Riemann sums So it's an important definition, and it's even more important that we can calculate it very easily later. So we'll do that this lesson and next lesson. But the definition, as usual in this course, is in terms of limits. So we take a function f on a b. So a number I is the definite of f over ab if for any epsilon greater than 0, there exists delta greater than 0, such that for all partitions P, and we said we wrote this for short just as a list of numbers. So if the partition is small, and for any ck, so these ck, remember, are chosen one in each of the intervals, we have that the Riemann sum is close to I. So I'm actually going to put brackets around this. So we take the Riemann sum and we subtract I and we take the absolute value and we make this less than epsilon. So what this is saying, idea, let me write, this here is the Riemann sum. What's the idea? Can make Riemann sum as close as we like to I by just making the size of the partition delta p small. I said delta p, that I didn't mean that. I meant this thing, which means the largest interval in the partition. Just making that small. The choice of intervals and CK does not affect this. Okay. Okay, so that's the definition. Now let's give some notation. We have a special notation for I, which has been around for a long time. We have an integral sign. We put the endpoint of the interval at the top and the bottom. We write the function fx like this. So this is called the integrand. This is the integral sign. X is the variable of integration. Or the dummy variable. And what else? So these we call limits of integration. And we say this is the definite integral of f. Okay, I'm just going to see if there are any questions. Okay. So note can change the dummy variable. So if I have the integral fx dx or the integral fu du, get the same answer. Same answer I. That's why we call it a dummy variable. So another note, so the limit above is more complicated than those from earlier in the course. But if it exists, we write for short that the limit, as the size of the partitions goes to 0 of the Riemann sums, so these are the Riemann sums, we write that this equals I. Okay, so now we defined it, let's start to calculate it. And the first step is to say when it exists and it doesn't exist. So let me just give a theorem. We won't give the proof, but if f is continuous, on AB, then its definite integral exists. So note this theorem, which we don't prove, does not say how to calculate the definite integral. We do this next. But the theorem is not too difficult to prove. The method is to consider the upper and lower sums that we mentioned last time and show that they converge to I, that they have limit I. Okay, and as I said, we will do this with antiderivatives. But it's important to say that not all functions are integrable. And we'll just give one example. So the function fx defined on the interval 0 to 1, which is 1 if x is rational, and 0 if x is not rational, is not, well, let me be precise, has no definite integral. So why? So for every interval, in particular these intervals, xk minus 1 to xk, we have ck in that interval, where ck is rational. So, taking any partition, can choose ck such that fck is 1. And that implies that the Riemann sum, so this is the sum over all the intervals in the partition, fck, times the length of that interval. Well, if all those are 1, then this is the sum of the length of all the intervals, and those add up to the big interval, 1. Because this is the length of the interval 0, 1. But also, have ck in this interval where ck is irrational. And that gives sp equals 0. And by the definition of the limit, if it exists, then the Riemann sums have to be close to something. However, we pick the partition in the CKs. So limit cannot exist. So that shows that not all functions are integrable. But also, we can have integrable but not continuous functions. Actually, let me save that up until I've given a simple example of an integral. I'm going to put this a little bit back. So let's put this simple example here. So example, fx equals c is a constant on the interval ab. Now for any p, have sp is by definition the sum over all the subintervals of fck. So I'm going to change the name of my constant so it's not confusing. Let's change the name of the constant to d. fck times the width of the intervals. Okay, I see there are some questions, so I'll stop and answer those in a moment. Oh, it's about the non-integral example, I guess. So all these are d. And remember when we make a sum with a constant multiple, we can take that constant multiple outside the sum. Like this. And we get d times the length of the interval b minus a. Okay, let me check these questions. Thank you. Sorry, yes. So I made a mistake. I need not rational here. Let me write that in and then we can take a break. Okay, yeah. So the symbol Q means rationals. So we're in the rationals or not in the rationals, in the rationals or not in the rationals. Sorry, that was confusing. I hope that's corrected, that misunderstanding. Let's take a break. Battery is low.
Oh, okay.
So I'm going to okay. Yeah. Okay, let's start again. So we saw that the integral, or say from 0 to 2 of a constant function let me just check how I wrote this. Yeah, let me add something up here. So using notation above, we have that the integral from a to b of this constant function d is d b minus a. Okay, so let's give an example of that. That, for instance, if my constant is 1, then I have answer 2. So the function in this case is 1, like this. But suppose we have another function fx, which is equal to 0 if x is between 0 and 1, half open interval, but 1 for this closed interval. So the graph now looks like this. So 0 here, but 1 here. Like this. And then this is actually integrable. And the integral from 0 to 2 of this fx is equal to 1. So you can check that with partitions. I just want to give an example that shows that all continuous functions are integrable. all continuous functions are integrable. But not all integrable functions are continuous. Okay, so now let's start to compute some integrals. So let's start with an example. Compute the integral from 0 to b of x and find area under graph of the function x on the interval ab. Now, it's quite easy to find the area under that graph because it's just a triangle. But I'm going to make a definition of what that area is. So definition is non-negative means this, and integrable over AB, then area under the graph A is defined to be the integral from A to B. So the first method is to use Riemann sums to calculate area. So let's take a partition P starting with 0, then 1 over n, then 2 over n, sorry, I mean b over n, and then 2b over n, all the way up to nb over n, which of course equals b. So 0 here and b are the endpoints of the interval. Now, we have that all the intervals are size b over n in this partition. So the Riemann sum, SP, it's a sum from k equals 1 to n of the value at some ck times the width of the interval. And I'm going to pick my ck to be at the right-hand end of each interval. So if I do that, the Riemann sum will be this. It will be kb over n times b over n. So for instance, for k equals 1, I've picked the right-hand end of my interval, that's b over n, and so the value is b over n. But the value is 2b over n for k equals 2, and so on. So, let's work out what this is. So, in this sum, b and n are constant. So I can take them out like that. And I get k inside the sum. And then we saw how last time to calculate that sum, it's half n times m plus 1, I think. So I'm just going to check that. If n equals 1, the answer should be 1, and it is 1. Okay. And so that is b squared over 2 So if n goes to infinity, we have smaller and smaller pieces, and then the size of the partition goes to 0. And it follows that if p goes to 0, then the limit of SP is b squared over 2 times 1. See, the n is going into infinity, so b squared over 2. And so looking back, so the area under the graph, it's just off the screen, but let me get it back. So the area under the graph, A, the integral from 0 to b, the function is just x this time, that equals b squared over 2. Let me move that up. Okay, so we got that by working with Riemann sums, and that worked for that example. But in general, we'll have to use antiderivatives. And this example, we can also use another method. So now let's look at the graph. So if this is B, so this is the graph, then this area, this is B as well. The area is, of course, B squared over 2. Because fx equals x is non-negative, on the interval 0 to b, and continuous, which implies that it's integrable, have that the area, which is b squared over 2, equals this integral. Okay. Why is FCK KB over M? Okay, let me be more explicit. So make some space. So each CK is in the interval xk minus 1 to xk, and that means in this case that CK is in k minus 1 b over n to kb over n. Do you see that? So these are x0, x1, x2, up to xn. And so using those definitions, CK is in this interval. So we can take ck is kb over n. That's what I mean by the right-hand end. So the right-hand end is this number here. So we could also take the left-hand end and we would get the same limit. Right. Okay, so let's give another way to think about definite integrals. We can think about them as areas. And we can think of them as related to averages. So average values. So definition, if f is integrable on AB, then its average or mean value is average of f is 1 over the length of the interval times the integral on that interval. So a simple example, f of x equals x on 0 to b. So the average of f is 1 over the length of the interval, which is just b this time, times the integral from 0 to b of x dx. And we saw that that is b squared over 2. And so the answer is b over 2. And that makes sense, looking at this graph, of course. So the average value, b over 2, is here. Okay, but we can do more difficult examples. If fx is the square root of 4 minus x squared on minus 2 to 2, so this one we know well. So it's half of a circle. And we know the area here. The area is 2 pi. So it's half pi r squared, that's half 4 pi. So the area is 2 pi, and so because f is non-negative, have area how to write this? So have 2 pi equals area equals the integral from -2 to 2. But we just defined, so the average of f is equal to 1 over 2 minus -2 times this definite integral, like this, and so we have 1 over 4 times 2 pi. We get pi over 2. So the average, let me draw it in. The average is what? So 3.1 something over 2 is 1.5 something. So actually, let me bring this back down. So the average, if this is 1, is something like this. But next time we'll be able to calculate these things for many other functions. So now let's start, just for the next minutes, on some rules. So rules for definite integrals. So the first one, constant multiple, that if I have an integral of k times a function that I know the integral of, then I can calculate that just like this. So for k constant. Okay, so let me put in some picture of this. Okay, we have all the pictures together at the moment. Let me rearrange this. Okay, so we have here a picture for the constant multiple. here. So why does that make sense? If I have the graph y equals fx, and I know the integral of that, so this graph is non-negative, so the integral is the area, the blue area, and I want the integral of y equals 2 times that, then the integral is going to be twice. So you can see from the picture that the area is going to be doubled. Okay. And so now I'm going to show some of these other pictures. Let's do sum. So, okay, that's the right size. Yeah, so sum is saying that if I have two functions f and g, and I add them together, then the integral is going to be the sum of the two integrals. So if I add them together, then I have to add two integrals together. And that makes sense from the picture because areas add. So sum that the integral from a to b of fx plus gx is sum of two integrals like this. Okay. And one more. So this one here, additivity, this is saying that areas add in a different way. So areas add when they're together left and right. So here I have an interval a to b and then an interval b to c. If I have two integrals on these intervals, then adding them together gives the integral on the big interval. So we call this additivity. And it's saying that if I have a less than b less than c, then the integral from a to c is a sum like this. Okay. So note these can be proved using definition of Riemann sums. So we're working through this picture, different properties of the integral. So extending the definition of so 2 points. The first point for A equals B, we say integral is 0. So this is the picture up here. How to write it? Yes. So a 0 width integral. So that makes sense because the area on that interval of 0 width is 0. And so we write integral from A to A of fx dx equals 0. So, so previously we assumed that A was less than B. If it's the other way around, let me get this right. If B is less than A, define integral to be negative. Of previous, that is make some more space. So how does this go? Yes, if B so if I have the integral from A to B, I've been assuming that A is less than B. But if B is less than A, then we define that integral to be minus and I always need dx's in here. this. Okay, so this gives another integral rule. Okay. So there's another few rules for integrals here in the picture. We'll do those next time. But for now, let's do some examples of what we have already. So examples. Suppose that I know that the integral from -1 to 1 of fx dx is 5. And that the integral from 1 to 4 of fx dx is -2. Then without knowing anything about the functions, I know that the integral from 4 to 1 of dx, so by this minus rule, it's minus the integral from 1 to 4. And so that's minus minus 2. And I can also calculate the integral from -1 to 4 of fx dx, because I have -1 to 1, and then all the way up to 4, and I know the integrals on these subintervals. So the formulas get quite big with these integral signs. So I can put in these values, 5 and -2 equals 3. So there are lots of calculations I can do like this. And one more example. If I have a to b x dx, what does this equal? If I assume that a and b are on opposite sides of 0, well, by that rule I just used, I can split this into two integrals like this. Oh. Apologies, I'll just finish this. So I have two integrals. The first one I don't know, but I can change the order of the limits to get that. 0 to a, which I do know, so minus a squared over 2 plus b squared over 2. Okay. So these are just the simple examples we can calculate so far, but we'll be able to calculate lots more and then use it. Okay, thank you.